Hello, seventh grade. It is week 13, and we are finishing up our study of continental drift and the evidence that has led to both continental drift and seafloor spreading as being accepted in the scientific community. So, by the end of this, we hope that you'll be able to explain seafloor spreading, which is a new hypothesis which we will be discussing today. So, first of all, who is Harry Hess? Harry Hess was a geologist and Navy submarine commander during World War II. Part of his mission had been to study the deepest parts of the ocean floor. He commanded an attack transport ship during World War II. He was intrigued by the seafloor maps produced by the ship's echo sounder. He thought about all the evidence for continental drift. He thought about all the unusual features of the seafloor, and he found the mechanism to explain them all. World War II allowed scientists to make some puzzling observations. The observations came from the seafloor bathymetry and magnetism. These observations include the fact that the seafloor has a large mountain range running through it. Deep trenches are found far above the ridges. Guyots have eroded tops that are deep below the sea level. They also found that the magnetic polarity of the seafloor changes. The center of the ridge is of normal polarity. Stripes of normal and reverse polarity are found symmetrically on both sides of the ridge. Also, the youngest seafloor is at the ridge. The oldest is further from the ridge. The oldest seafloor is much younger than the oldest continental crust. Scientists needed to be able to explain these observations. Not long after Wegener's death, scientists recognized that there is convection in the mantle. Deeper material is hotter, and so it rises. Near the surface, it becomes cooler and denser, so it sinks. This creates a convection cell in the mantle. After the war, Henry Hess put together the ideas and evidence he needed. Hess resurrected Wegener's continental drift hypothesis. He reviewed the mantle convection idea. He thought about the bathymetric features and the patterns of magnetic polarity on the seafloor. In 1962, Hess published a new idea that he called seafloor spreading. He wrote that the hot magma rises to the Rift Valley in the mid-ocean ridges. The lava cools to form new seafloor. Later, more lava erupts at the ridge. The new lava pushes the seafloor horizontally away from the ridge axis. The seafloor moves. Magnetite crystals at the lava point in the direction of the magnetic North Pole. The different stripes of magnetic polarity reveal different ages of the seafloor. In some places, the oceanic crust comes up to a continent. The moving crust pushes that continent away from the ridge axis as well. If the moving oceanic crust reaches a deep sea trench, the crust sinks into the mantle. The creation and destruction of oceanic crust is the reason that the mantle moves, or it's the reason that the continents move. As you can see in this picture, the gray oceanic crust in this picture originates in the center where the two plates are moving apart and magma rises to form new oceanic crust. This causes seafloor spreading as well. And as the oceanic crust pushes to the left and runs into continental crust, the result is folded mountains. The continental crust gets crushed and pushed upward, forcing existing rock up into mountain ranges. This is what happened in the Himalayas when the Indian continent crashed into the Eurasian plate. On the right-hand side, you see oceanic crust in gray again, arriving at continental crust, but instead it slips beneath the continental crust. And the continental crust rides over the top of the oceanic crust. This is known as a subduction zone, and this is where you would find trenches as well. Because it's forced down into the mantle, the crust melts. The added pressure adds to the magma located beneath the surface of the continental crust, and that magma forces its way up to form coastal volcanoes, as can be seen on the Pacific coastline. Washington, Oregon, California, Mexico. As oceanic crust moves away from the ridge crest, it pushes a continent away from the ridge axis, as seen on the left. If the oceanic crust reaches a deep sea trench, it sinks into the trench. In other words, it's forced underneath the continent, as seen on the right. The oldest crust is coldest and lies deepest in the ocean. The flat-topped guyots were once active volcanoes that were above sea level. They were eroded at their tops. As the seafloor moved away from the ridge, the crust sank deeper. The tops of the guyots went below sea level. Seafloor spreading is the seafloor spreading is the mechanism that Wegener was looking for. Convection currents within the mantle drive the continents. The continents are pushed by oceanic crust, like they are on a conveyor belt. Over millions of years, the continents move around the planet's surface. The spreading plate takes along any continent that rides on it. So, in summary, the seafloor spreading is a mixture of different ideas and data. Continental drift and mantle convection are supported by bathymetric and magnetic data from the seafloor. Harry Hess called his idea an essay in geopoetry. This could be because so many ideas fit together so well. It could also be because at the time, he didn't have all of the seafloor data he needed for evidence. Seafloor spreading is the mechanism for the drifting continents. So, if you are able to explain the seafloor spreading hypothesis, please go on to the next activity. If not, feel free to go back and review the video one more time. Have a great day, and we'll talk to you later.